Firstly, thank you all very much, and thank you AnchorCom for allowing us to be in this excellent cooperation. Carsten, Karen, thank you very much. As we're here, we've been here and waiting a long time to sort of get back to meeting each other, saying hello, where we are, what's going on. I'm so appreciative to be able to be here and be part of this great cooperation, being part of this and making this panel what it is. A little bit about myself. President for the SCTE, Chair for Modernization, Vice Chair for Training, Vice Chair for Training Standards, sit as a convener on the standards, Chair for the SCTE Limited, CSO and Head of Sales when on board for the BTV group at PKT. And I've got 3 decades in broadband. Not to take this time away, Georg, would you like to come up and introduce yourself and take your presentation?
Hi, welcome also from my side. I'm Georg Heiler from Austria. I have to start with a disclaimer though. The legal department told me that I have to make it clear that I'm not talking for Germany or Deutsche Telekom, but rather only for the NatCo in Austria here. With that being said, this is not only a project that we're working on in the company, but rather a collaboration with a research institute. I'm also a doctoral PhD student at the Technical University in Vienna, and this was a joint collaboration between both entities. Let's see if a clicker actually clicks. Yes. So I want to talk about high noise issues in the network. I think most of the people on this conference might be familiar with the problem. We have issues that are detected at the root of the topology of the network. The CMTS will showcase that we have a problem somewhere in that specific fiber node area. But we will not be able to exactly pinpoint one specific device as the root cause. As the problem might propagate up towards the fiber node from one device, more and more can be affected. In fact, the customer impact can be fairly severe, such as no service will be available in that specific network segment for other users. So the task that we want to work on is we want to make this search procedure faster, as the time that is spent on the ticket, or the money that is allocated should be reduced, but also that the downtime and the inconvenience for the customer is decreased. The current process that was in place so far was manual binary search procedure, so basically starting from the root. The technicians went down into a field, walked around, drove with a car, and tried to turn off and on specific devices and follow the path of the noise. Obviously, this is not ideal, because it's lengthy, but also, at least for some specific amount of time, turns off the internet for users with high-quality network connectivity. So we started simple with a baseline model. This is the term we would use in data science. Perhaps more coming from the broadband perspective, we're using the business experience of the operations department. What you can see here on the screen is a screenshot from the monitoring tool for a specific, very easy to recognize condition of the high noise problem. We observe that the signal to noise ratio is drastically dropping when an incident is going on in the network. And we can observe that the corresponding TX values of the specific offending modem is increasing. And there's a correlation with a specific incident and the root cause. This is something which looks really clear here in this case, and it works in some cases, and this serves as a baseline business rule already quite well and much better than the previous process. Where does this problem originate from? Well, corroded connections, but my technicians have also told me that new, fresh connectors might still showcase the same issues. So perhaps one of the following talks, talking about better connectors in the future, might be able to alleviate some of the problems there. We can not only work on the identification of a problematic device, But we could also store the results here. As you can observe, this simple solution is not coupled with a direct like incident or ticket, but rather it's automatic in the sense of any like SNR change in the network would trigger such a root cause search. This means in case there are flaky regions in the network, it would allow us to cluster the data, for example via a heat map, and in case a technician is in a specific region anyways because some device needs to be upgraded or fixed, they could use the spare time to actually do house cleaning procedures in that region to increase the overall quality of that specific region. And thus, as we are already there, reduce time and money to actually go to this location, and over time increase the quality of the network. This second thing is only outlined so far. We are only envisioning this procedure, but it would be a really interesting step towards the future. That being said, it is not always that simple. Sometimes, and in fact fairly often, this simple business rule does not work. So we see that some incident is ongoing from the measurements of the SNR, but the simple rule that is showcasing that a specific TX spike should be related with a specific incident is not correct. We observe in red the TX values for the modem that later by manual analysis of Fieldforce colleagues was identified as the root cause. And here, compared to the initial very picturesque plot, you can see that the simple business rule doesn't work. So this means we need to change something in how we work with the data. Having a background in data science, I would say simply let's train more models. But this is where the first problem already starts, getting the right data. I will talk about how to get the data in a minute. We observe multiple levels of proactiveness, or how this task could be handled. The first level is a topic that I already explained as a baseline business rule. It's very simple and understood by the existing operations department and business units. Here in our case, it was the largest TX change shortly before the incident detected by the SNR change, but it can fail in ambiguous situations. The next level up would be to increase the AI assistance by working with a model that works well also in complex scenarios to steer technicians directly to the root-causing device. The idea is not to have a hard-coded business rule, but rather a model that can learn from the data. In order to do so, we will see later the details, we have to ensure that we get an end-to-end feedback pipeline working. And the third and more envisioned path in the future could be more of an insurance approach, where we could try to predict an incident in the future and perhaps try to send out and dispatch technicians proactively, but it will be a rather hard way of also validating the success, given that we are a very cost-driven business, and evaluating the quality of fixing non-existing incidents, especially in the operations department, will be hard. So for us, we see as a telco that the second approach might be a sweet spot, and we want to evaluate how this one goes further. The overall goal is to always improve the network quality to make the customers more satisfied and also reduce downtime. So how does the data pipeline look like? We are working with multiple systems that are and were separate so far in the business. On one hand, we have the topology of the network. In fact, I have to admit it's not even available, the digital topology for the whole part of the network. So we are focusing our analysis here only on that part where we do have a full topology available. We have technical alarms that are triggered by the monitoring tool in the network and passed through and operated by the network operating center. We have the HFC telemetry data detected from our existing cable monitoring plant solution. And we have a feedback from the technicians in the field. As you can already imagine, the data is probably not linked up like in an Excel sheet, but rather we have different notions of time, not a single primary key where you can join it together. And in particular, perhaps the feedback might not be noted in an easy-to-use way. In our case, it turned out it was rather free-form text fields, so we had to apply some data cleaning magic here. In the end, we end up with a specific session of incident data. We were focusing on 72 hours before the incident of telemetry data leading up to the incident, and the feedback of the technicians, what device participating in that specific fiber node area was the root cause of the incident. So here I'll try to visualize this again so that you have really picture in your head how the data is structured so that the models later on can learn and optimize from the data to figure out where to send the technicians to. On one hand, in the x-axis, we see basically time as an abstract notion of time where we have the state of the last 72 hours of telemetry data in the network before or leading up to the incident. When we have many devices, all devices in that specific fiber node area region, and we have multiple metrics for each of the devices, being SNR, TX, and all of the like P&M matrix you can imagine here in an aggregated way at the level of a last line amplifier. As this was the topological level, the feedback was available. With this now, the incident session window, in the context of a feedback, we have data in a way that we have end-to-end feedback pipeline that is part of a regular business processes now digitalized. And we can from this point onwards start to train computational algorithms and models to optimize the steering of the technicians. So this is the hard part, basically the part that the vendors usually don't cover when they present a shiny machine learning solution. Making the data inputable and building the feedback loop. The second step is training the machine learning classifier. There, you could potentially even rely on automatic machine learning techniques being developed in the field. We were trialing several approaches from the baseline business rule to some traditional simple statistical models to very well-established models in industries based on tree boosting algorithms and some very modern and fancy deep learning algorithms. It turned out that simply applying the model and getting a prediction was not enough. We added a third step in the pipeline. As you can guess, the network is quite heterogeneous. This is why we need to basically apply sort of a softmax after the output of the models. What is softmax, perhaps, in this audience? Basically, we ranked the output probabilities of a device being a root-causing candidate. And why is this good? Well, each incident has some specific intricate dynamics. It's very hard to normalize the data, so the model has data that is comparable across incidents and to generalize and learn from. But by applying the ranking procedure, basically the dynamics of this incident are sort of accounted for and works very well for our models. What we observed is that the models, or the best models, were in fact more than 2.x better than the baseline business rule. What you can see here is a comparison of many models, but what you should take away are a couple of simple facts. First of all, any model was better than that simple basic business rule. Very, very fancy models like neural networks used for deep learning could potentially be really great in the future when we have more and better quality training data, but due to the data acquisition process I outlined, we were stuck with what we had. And it turned out that none of the neural networking approaches really improved dramatically. What we, however, could see is that a gradient boosted tree-based algorithm that can work really well and is easy, also simpler to use and optimize, could understand this suboptimal training data quite well. In fact, led to this great improvement over the baseline model. In the future, in particular with the university collaboration and some master student, we are pursuing the analysis of that third level of proactive analytics, the insurance approach. Here, the idea is really to predict 1 to 3 hours or perhaps 8 hours in advance if something will go wrong. It's still in an early stage research, but we will update the scientific publication once we know more how well it goes down the line here. What's important to understand here, we are here not predicting a specific incident, but rather using CER, thresholded observations, so it's very generic. Let me summarize the findings from our approach here. First of all, regarding data quality. The hard step is to build an end-to-end feedback loop so that the feedback part of existing business processes can be used for any machine learning project. This is in fact not particular to our project here, but for generic, any machine learning project you might pursue. In our case, it turned out that perhaps in the future deploying an mobile app for the field technicians where they could use a drop-down field instead of a free-form text field to enter the data of a broken amplifier might be able to drastically improve the quality. Secondly, in our IT and data processing domain, we are working towards a streaming or integrated approach. We do not want to conduct data archaeology, where we have disparate systems and later, post hoc, after the fact, want to tie the data together, but rather we want to be able to react to events, and where we obviously know we cannot do everything on our own. We rely on some vendors opening up their interfaces and integrating these various tools you have seen before. They are not a single vendor solution, and here analytics was also not part of a specific vendor, but rather our own. So we want to encourage vendors to support us and make it easier to integrate the data from these various black box systems into a central streaming solution. Furthermore, we have rolled out the simple business rule so far. We have showcased in the research project that dramatic improvements can be made with machine learning by a factor of approximately 2. We are experimenting with the forecasting, and perhaps even for the simpler approach, the heat-map-based clustering could be used to reduce flaky cases. If you want to learn more, you will find the QR code here or the link to the slide deck, also to the scientific publication. And with that being said, I hope I can encourage you to try some machine learning on your own data sets.
Thank you very much. Having been a technician in the field, I would love to have had some of this around me every once in a while. So it would have helped a lot. Nick, would you like to present yourself? And then we can go through your presentation. Any questions, we'll take them at the end. There's 2 microphones either side, so please use them and come with some good questions. Thank you, Nick.
Hi there, my name is Nick Padfield. I work for Amphenol Cabelcon as product engineer. I've got 20 years experience in RF, wireless and broadband. I'm here to talk to you today about the humble F connector. Grab the clicker. So the F connector has been used in the cable TV industry since the 1950s, and the dimensions and performance standardized worldwide by the SCTE. The F connector and F connector port are defined to operate up to 3 gigahertz, but for DOCSIS 4 operation, we're looking for good quality performance up to 1.8 gigahertz, which gives the potential to achieve 10 gigabits per second download speeds and 6 gigabits per second upload speed. So in terms of quality of the connection between the modem and CMTS, this could be defined as a signal path that is not being impacted by noise or external signals disrupting the wanted DOCSIS signal. So in the DOCSIS standard, there's the ability to adjust the modulation scheme being used between the cable modem, CMTS, to maximize data throughput based on the quality of the connection. So in simplistic terms, the lower the noise and interference between the modem and CMTS, then the more complex and spectrum-efficient modulation scheme can be used. So the higher the noise or interference, then the less complex signal must be used, limiting the data throughput. So as more complex modulation schemes are being used, which is the big push for DOCSIS 3.1 and now DOCSIS 4, that there's the ability to adjust it. So any unwanted or issues, unexplained issues on the system, as Georg talked about in his, that are being defined, can actually highlight that there's some ingress or egress or some issues with the channel and put it into a lower throughput state, or worst case, that it can completely fail. So just to sort of finish the introduction, so Cabelcon has received sort of jumpers over the years where sort of no root cause has been found from the returns of sort of devices to us. In the later years, these have been increased as sort of the modulation schemes have been more impacting and there's more information to look at. So each time we received sort of these returns and looking at the information from the customers, we started to have new approaches and sort of look into some of these issues in more detail. So in this talk, I'll give you a tour of the findings, the data, and our solution. So here we have an X-ray of what we'd all hope to see with every F-connector connection, a perfect port with a nice RF flat face, and a connector with well-defined threads on the port and nice well-defined threads on the nut connecting it. And over the top, just sort of added a bit of a filter just to try and highlight what's going on. So this is what we'd like to see on every tap or every RF connection that's out there. So the feedback that we've been having from customers was specifically, the big one was always ingress. There's something being detected. There's some noise or unwanted signals being detected in the network. So these could point to various things, loose connectors. More extreme cases, there's water penetration where you've actually got moisture getting into that physical connection, which could, essentially end up with the deterioration completely of that connection. And these are kind of shown as various pointers, widely called ingress and egress, but, these could be noisy return path or unstable performance where, unexplained things happening that signals would drop and come back. So it was a whole multitude of things that were being seen that couldn't be explained very simply. And one of the main reasons is probably the variation of F-port interfaces being seen out there in the market. So here's a range of readily available ports that are out there, and you can see from the sizes and the shapes that there's a wide variation out there of what a standard F-port looks like. And here's another filter over the top. So this highlights some of the sort of difference in surface finishes on the F-port, so where there's sort of scarring or indents, or just highlighting that sort of volume of the front face of the surface. I've got a few slides of just some examples of some real close-ups of what we've seen from the field, and it's sort of indicative of what comes back and what we've had to look at to try and ensure that we can have a good quality sort of F connection in the future. So this is something that we've seen. So you can have various things that we've seen as poor front face offset on the connector. So it's not central. There's a bit more material on one side than the other. And this could cause, the F connector being put on not to be in a straight position. And also the shape of the threads also can have a big bearing on what's seen. And how well the connector or the interface that you're adding to this would work. So in this case, these are very thin U-shaped threads on the port, which could lead to, poor connection between the threads on the nut. And other things we've seen, with that front face, you can get very narrow pieces where the actual front sort of volume of, or the surface area that's available to connect to the F port that's being added, or the F male connector, and again, sort of variations in the thread. And even further, these are some of these are sort of new parts from the field that we've seen. So here's a front interface. It's a nice wide surface area, but there's some quite extreme scarring on there. And also, in the same extreme case, even when fully torqued up to nothing more than sort of 40 inch-pounds, which is at the top end of the SCTE specs that these ports should last to, we get threads that are actually stripped off when the nut's tightened up. And again, various ways that ports are made. Ports can be made by casting, or they can also be made by machining. So when ports are cast together, there's two halves, so you can get sort of casting lines in the front surface, or even more extreme scarring that we've seen here. And all the time we're coming back to what we use in the lab and what we'd expect to see with sort of all the large operators and everybody out there. These are the style of ports that you expect to see out there that are being connected to. So, well-machined ports with a front flat interface, well-defined threads, with a material that has the hardness to cope with being torqued up with a nut. So this is what came back to when we have our returns back to us, or here's a cable jumper that's being sort of blamed for causing issues in the network. When we come back to the lab and test it on a port that is expected to be seen, that we don't see a fault found. So it caused us to just dig a little bit further. And again, we're talking about material properties. So again, a sort of zinc, copper, nickel alloy, nickel brass connector. There's, again, a wide range. So I'm not going to delve very deep into the metallurgy, but as you increase the composition with zinc inside the alloy, you can affect the hardness. So the first three is where we can see that the hardness is increasing with the yellow dot as the zinc level is increased. So as the zinc in the compound or the alloy is increased, you can actually oversaturate the alloy with zinc and it suddenly becomes very soft. So it's not only the metallurgy, but it's also the definition of the mechanics which can affect how well the port will function in the field. So a very quick summary. So what we found is these defects result in poor matches of the interface. So you can get tilted, offset connections, and this can all point to this ingress and egress and issues in the network. So this was a highlight that we needed to look really deep into what needed to be done to improve this and how to solve the issues. And through several years of experimentation and looking at various solutions, a very small change to that front port of the F connector can have a big impact on how we can work with all these different sorts of variations in the F ports out in the field. So the front insert has been made conical, and this helps to self-center the F connector on the various ports that it's seeing, and it can even help to overcome some of the defects that we're seeing as well. So I've got a few slides of just looking at how a sort of standard port will go onto a connector interface. So this is sort of a stripped back of what the connector is, so the nut's removed, and this is purely the center of the connector looking on various ports. So in this case, you can see that on the left-hand side is the connector itself, and the right-hand side is the port. Actually, there's a little white glint in the middle in that interface, and that's basically where the RF isn't sealing. And you've got a potential source of ingress. So even though the connector could be torqued up fully, there's still a gap in there that could leak RF. And here we have the same interface of the port with the conical interface, and we can see that that gap has been removed, and there's a 360-degree RF seal now in that connection. And through these measurements, we had to quantify, are we making improvement? Are we making things better? So there were various measurements done to look at sort of resistance of the port. In this case, we took some measurement points on the RF connector and the port. And we're looking at how the different styles of interface react with the port. So here we have a repeated measurement of 6 different ports with a large flat interface on the connector, a narrow flat interface, and the conical interface. And in that order, you can see that overall the conical interface led to a low resistance. So this isn't, the final resolution of this is definitely a better interface, but it, again, all points to these ways of trying to make measurements and understand that the changes that we're making to the connector are for the better. One of the big pieces that we saw with the connector was material displacement. So here's a view of a port. On the left, we have a sort of non-flat face. It's not 90 degrees to the threads. It's fairly central, but again, what we can do is we can put the conical interface on, and actually the design of it and that cone on the front of that port that we're adding on, by torquing it up to 30, 40 inch-pounds and removing it, we're actually doing some material displacement in the port. The hard brass connector and onto the less hard port means that there's that material displacement. So we can actually change the interface a little bit by adding the connector and the forces applied. I have 3 or 4 X-rays, again, just showing how we're just trying to show that putting this conical interface on these ports can overcome some of the issues. So here's an X-ray of a port with the casting lines in it. So this was showing that there's some slightly high points on the interface. And actually, again, we get gaps where there's not a full 360-degree seal because of those high points on the port. But when we use the conical interface, because of that shape of the front end, we're actually displacing some of those casting lines and actually making a 360-degree seal. So we're then making that connection RF tight. And again, some of these other defects that we've seen where, again, with castings, they might not be perfectly matched together, so you get almost a step in the front interface. So that can cause a few defects or some few faults in the connection, causing nuts to not be on correctly onto the thread. So, you know, all the forces are not applied evenly to that front face, causing a good RF connection. And again, we can show that because of this conical interface, we can overcome some of these defects in that front face. And again, have that 360-degree RF seal, which is very important for ingress and egress. And again, just trying to highlight, you know, we haven't just looked at one port or one interface, that we're trying to have a big variation of what we're looking at to make sure that all these different things that we're seeing out in the field can be improved or at least helped with changing the design of the connector. And even some more extreme examples, like a 2-degree sort of angle on the front. Again, we're not going to completely overcome every sort of issue that we're seeing in the connector ports, but from the multitude of things that we've looked at with this connector interface, we show we're an improvement, and all the time trying to get to the point where we're trying to get rid of some of these sort of issues and show that we're making an improvement and continually sort of improving what we're doing. Another things we've done is being able to quantify some of these things in terms of measurements on shielding effectiveness. So here we have sort of the baseline of the measurement system, and here we have that interface with the high attenuation casting lines on it. So we're seeing that, you know, even with the same connector and the same interface, that we are seeing a degradation of that performance. And again, using the same port but with the conical interface, we can show that we can get back to that baseline of a sort of perfect connection. So before I go too far over time, I will do a very quick summary. So we've tried to show very briefly here that by keeping the connector within the confines of the SCTE specifications, but having a subtle change to that interface, we can overcome some of the issues that have been seen. You know, we have that self-centering, we have a small material displacement, especially with the hard brass connector, and that can help with some of these softer materials on the ports. And overall, we're just trying to make a better mechanical, which therefore leads to a better electrical connection as well. So thank you very much for your time, and I will stop there. Thank you very much.
Thanks very much, Nick. It's nice to see a connector from the 1950s can get some innovation put into it 70 years later. Arttu, would you like to come up and present yourself and take us through your presentation?
Now I guess it's better. Yeah. My name is Arttu Purmonen. I'm heading marketing of Teleste Networks, and I know that many of you now, when you heard the word marketing, you will shut your ears. But do not be worried. I'm 100% engineer, and you, after my presentation, you have so many decibels on the floor that you have to call someone to clean them. My idea was to shortly go through what it means to move to high-split upgrades in today's cable networks. What we see today is that many operators are moving from 65 up to 204 high-split networks. And based on those experiences that we have, I will share some insights. So my idea is to have this kind of 5-course meal. Most likely some of those meals are familiar to you, but probably some of them might be new and you will get something new as well. So before jumping to the courses, why high split? And why especially with distributed access architecture? Well, first of all, there is upstream traffic growth in average. That is something which we have discussed, or the industry has discussed already several years. But then there is also this upstream peak traffic growth. And although these two things are, let's say, intertwined, they are not exactly the same. So what we can see is that some operators, for example, might have consumers wanting to, for example, let's say more than 50 megabit upstream. And in those cases, you cannot allocate the whole upstream for the single customer. So these, although the average rates would be still decent, some heavy users might force you to think that what to do with the upgrades. Obviously, you could go to 85 megahertz, but that brings only minor improvements. Then, of course, if you move from DOCSIS 3.0 to the 3.1, you get also better spectral efficiency, as you are able to use even up to 1K OFDMA, which after all is, of course, QAM signal, but OFDMA format. Then, of course, many operators have, if you are operating cable network, you have fiber to the home and fixed wireless knocking at your door, and you might need to do something because usually they advertise symmetrical access, whether you need it or not. Then, of course, combining diplexer upgrades, DA fieldwork and planning makes a lot of sense. If you are anyway going to visit street cabinets, why not to upgrade the amplifiers as well? In Europe, most operators already have 200 megahertz capable amplifiers, so all you have to do is change the diplexers, and that is something which we see that is ongoing at the moment. So I'm now basing all these calculations to the idea that you have remote PHY or remote MAC PHY there at the field. And here you can see the input levels, so not the node input level, but the RPD module input level. And what you most likely want to see when you are using the return path up to the 204 megahertz. So first you have there this yellow line, which is the noise, which we already heard. The two previous presentations were describing reasons why there are of course other reasons as well, but typically frequencies below, let's say, 25 or 30-ish megahertz, they are something which you are not able to use. Then you most likely have some single carry CAM, DOCSIS 3.0, because of your legacy modems that you want to keep there. Then after those single carry QAM channels, you have OFDMA block going a little bit, let's say, about 100 megahertz, and then you have the big OFDMA block there about 100 megahertz. And then the questions here are, first of all, that what kind of guard band you need between the single carry QAM and the OFDMA channel, and then what is the ideal level that you want to have into RPD, and what kind of modulation error ratio you can expect in your network. So first statement, I claim that attenuation is rarely your enemy below 200 megahertz. Here is an example showing what I mean. So basically we have cable modem. In this case, let's say cable modem is sending with 100 decibel microvolts because of the attenuation of the wall outlet, the drop cable, and the last splitter, and the cabling between the splitter and the amplifier. So in the amplifier output, although we now, of course, talk about return path, around 70 decibel microvolts would be ideal, so 10 decibel millivolts. The same comes with the RPD. So it gives, let's say, or it means that this 30 decibel leads to the cable modem sending with 100 decibel microvolts. So you have at least 12 decibel reserve, depending what kind of modems you have there at the field. So when you increase attenuation, you actually have higher transmission level, which improves your signal-to-noise ratio and modulation error ratio. So cable modems have higher signal level because they are compensating the losses of the last mile. So higher isolation and higher attenuation actually means that you have less problems, better modulation error ratio, and you can use more advanced modulation methods. Then also the isolation in wall outlets. If you have 200 MHz wall outlet or 204 wall outlets, you have to pay attention what is the isolation there. I would say that at least 50 decibel is needed, but today with modern components, if the wall outlets are manufactured in modern facilities, you can expect something like 60 decibel isolation. And that is actually something which you need because this cable modem transmitting to high level, that transmission leaks to the TV port. Now, of course, there is no signal or television signal below 200 MHz, but still TV tuners are receiving the signal also below 200 MHz. And if the level is too high, you are getting problems, and it's very unpredictable what actually, let's say, goes on there in the TV tuners. One question which we often get is that can you mix 200 MHz wall outlets and 65 MHz wall outlet? Here the logic would be that you are, let's say, your network is 200 MHz capable, but when the customer is asking, for example, very high-speed internet connection, 50 megabit upstream, for example, a lot of downstream, you give new cable modem, DOCSIS 3.1 cable modem with new wall outlet. So that home is then 200 megahertz home. And then in neighbor, you might have 65 megahertz wall outlet. What it means is that basically, let's say, the signal that the 200 megahertz home sends will leak through the splitter to the other home, which is 65 megahertz home. And that obviously is a problem for the TV tuner. And in those cases, what we actually see is that, well, first of all, in this kind of case, you obviously don't have any television services below 200 megahertz, but you don't have FM radio either. And even though you don't have FM radio, you might have FM ingress coming from those wall outlets that still have this FM port. So actually, if you have this kind of scenario, what we have seen is that operators actually are not using the FM frequencies for OFDMA. They are leaving them there, but they are not using that to increase the upstream capacity. So the first OFDMA block starts above the FM. Obviously, let's say it's away from the capacity, but naturally this kind of gradual upgrades are cheaper. So if that is possible and your competitor is not pushing there with fiber or fixed wireless, forcing you to actually upgrade more aggressively, then yeah, it's an option. Then the question was how about the needed quad band between single carrier QAM and OFDMA? We have been running these tests in our lab, actually a lot of, and what we have found out is that 500 kilohertz, so 0.5 megahertz between the single carrier QAM and OFDMA is enough. So if you have this 500 kilohertz there between, we see that modulation error ratio is perfect. You don't have corrected, or FEC doesn't show that it has to correct any bits. MER is excellent. MER is also excellent with the ATDMA channel, so with the single carrier QAM channel, that is the highest single carrier QAM channel that you have in your network. Then every now and then there is a discussion that, okay, fine, this OFDMA forward error correction is so effective that actually you could, let's say, use that forward error correction to squeeze this quad band, because the forward error correction is anyway able to fix these edge frequencies of the OFDMA. That would not be my choice, because the forward error correction is actually meant to fix issues that are unpredicted. So if you are already taking this margin out with too tight quad band, then you don't, let's say, have any margins left once something bad happens in your network. Then amplifiers and the upstream noise funneling. Here the question is that, okay, what kind of amplifier cascades are challenging, or are they challenging? Do they cause issues with the upstream? The thing is that we have been measuring this in the lab many times, and basically it can be modeled even with, here you see the calculation, and actually the real measurements and the calculation are pretty equal. They give pretty equal results. So because of the very high carrier to noise ratio of amplifiers, about 57 decibels, these amplifier clusters do not damage the upstream. So amplifier clusters, even long cascades, they are not a problem for upstream. If you have upstream issues, and if your amplifiers are adjusted perfectly, so they are totally transparent, I would say that those issues are coming from elsewhere in your network, but not from the amplifiers. So even long cascades, and now I want to highlight upstream. Upstream part works perfectly. With the downstream, and then when we go to the really high frequencies, there we do have separate issues. I have one caveat here. So this applies when you have cables, underground cables. Obviously, if you have outdoor cables which are exposed to direct sunlight, you might see some issues, but that is a totally different story. I'm happy to discuss it later on, but unfortunately I don't have time now to cover it. So in summary, isolation and attenuation below 204 MHz are your new best friends forever. Here I want to highlight my new hashtag BFF, which my daughter taught me, so it shows me that I'm still younger than 50 years. Then consider upgrading old wall outlets to 204 MHz capable as soon as possible. The needed quad band is only 0.5 MHz between the single carrier QAM and OFDMA channels, and even long amplifier cascades are not a challenge for the upstream. I hope that you got something from my 5-course dinner, so please contact me either directly via email or then visit our booth. I will be there. Thanks for your time.
Thank you very much, Arttu. Would you mind just clearing up all of the decibels over here? It's getting a bit crowded. Jay, would you like to take and present yourself and take us through your presentation?
Good afternoon, everyone. My name is Jay Lee, and I'm the CTO at ATX. I'm going to deviate a little bit from technical talk, and I'm going to talk a little bit today about a economic model that we worked on with a partner MSO customer probably about over a year ago, and it really explored or took a look at how MSOs might maintain their taps and passives portion of their HFC network with two different options. Maintain it the way they always have, which we would call a legacy mode, which is really as cost effectively as possible, or at least it might look as cost effectively as possible. Or the other approach, which is we call evolutionary mode, where you actually start to seed your network with, on every maintenance call, you start to take out existing taps and passive devices and start to seed your network with 1.8 gigahertz capable equipment. All of this obviously in the context of an MSO's journey to upgrade their network to be able to support DOCSIS 4.0 1.8 gigahertz. So I'll just talk a little bit about how we built the model. On the left side of the screen, we took a look at the maintenance drivers the items that really drive the maintenance aspects of the networks. One of the big ones was actually loose connections in loose screws in taps and passive devices. We also have failed faceplates where in a tap type device, if the faceplate fails, just the faceplate needs to be exchanged out. Or in some cases, we have full failure devices where a brand new device needs to be spliced into the hardline coax. And what we did is extracted from that two different approaches as to how we would deal with those maintenance mode activities. As I said earlier, one mode was what we called legacy mode. So that meant if a technician went out to fix a location that had loose screws, they would simply tighten the loose screws. If it was a faceplate that was damaged in some way, just the faceplate would be upgraded. So, and if a device had to be pulled out of the network and replaced, it would be what we would call legacy 1.2 gigahertz technology devices that would be put in, which would be less costly than 1.8 gigahertz type devices. And I'll go through some of our cost modeling in the next slide. From an evolutionary standpoint, what we modeled was every time a technician rolled up to a maintenance issue, whether it was with a tap or a passive, that device would automatically be removed from the network, and the entire device would be replaced with a 2 gigahertz capable tap or passive. The model that we generated was over a 5-year time horizon. So at year 5, the concept was that the entire taps and passives portion of the network would be upgraded with 2 gigahertz capable devices so that the entire network could support DOCSIS 4.0 1.8 gigahertz to its fullest extent. Just before we get into some of the details around the costs, this was one of the interesting findings in this study. This is actual data from one of our MSO partners. They had started to collect information on what the sources of maintenance mode activity was, and they actually found a 0.2% failure rate with respect to loose screws, either the screw down on the hardline stinger would back off itself, or technicians would forget to tighten it down. 0.2% doesn't sound like a lot, but as you can see in the table in the top right, depending on how big your network is, it translates to many truck rolls a day that are really, really potentially avoidable. One of the things that's a benefit with 2 gigahertz type devices or 1.8 gigahertz type devices, and not just ATXs, I think all of the manufacturers of taps and passive devices, to attain frequencies that hit 1.8 gigahertz or extend beyond, the actual mechanism with which the stinger from the hardline coax interfaces with the tap or passive device will not involve screws any longer. Most designs will be some type of barrel with a spring-loaded mechanism that would engage on the hardline stinger. So inherently, that's a huge benefit with respect to removing a legacy device and putting in a new 2 gigahertz capable device. That whole loose screw phenomena disappears. So just with respect to some of the modeling we did, I apologize, I thought I would have a pointer, so I'll have to talk through it. But in the top left is how we modeled a given MSO's network. For this presentation, we chose a 10 million homes passed network. The model's totally scalable, and by the way, we make it available to anybody who's interested. But from the number of homes passed, we basically had some estimates with respect to how that would manifest itself in terms of numbers of taps and passives in the network. We took number of homes passed, divided it by 4.5 to get to our number of taps as an example, and our ratio of taps and passives is a 3 to 1. So that's how we basically calculated this out in a 10 million homes passed network, where you can see our total taps are 2.2 million, our total passives are 740,000 for a total of almost 3 million devices in a 10 million homes passed network. As it relates to the failure profile we projected onto this network, we took in aggregate about a 1% failure rate. 0.2% of that was the loose connection side of things, and then 0.8% was whether it was a full device or a faceplate type of failure. We also modeled in that out of that 0.8% failure rate, that 25% of that 0.8% was actually a faceplate issue, as opposed to an entire device that would have needed to be addressed on a maintenance mode basis. On the right-hand side of the chart here, we basically outline the cost inputs associated with both materials and labor. And what we did for this particular exercise is we normalized all of the costs against what we call legacy 1.2 gigahertz tap device. So we called that device $1, and we extrapolated from that $1 to the other costs associated with the maintenance mode or upgrade activity. So as an example, you see a faceplate is 75 cents as opposed to $1. From a labor perspective, two key elements are on a targeted maintenance mode, on a targeted maintenance activity, we have that at 8 times the cost of, or $8.30, which is 8 times the cost of the tap material. And that's really when it's a one-off maintenance mode issue and a technician needs to roll a truck on a one-off basis. Another important cost we factored in here is the bulk rate to actually upgrade an entire node serving area, which would contemplate that technicians are rolled out to that area and upgrade the entire node serving area, and replacing or maintaining or replacing the taps or passives. The other important piece here is the 2 gigahertz taps devices we modeled in at a 30% premium over what we call the legacy 1.2 gigahertz. So when we ran this model, this is sort of a summary of of the maintenance activity that occurs in the plant over a given year. So in this, and once again, this is for a 10 million homes passed network. It scales linearly. We saw the total number of location visits at almost 30,000 in a given year. And you can see the breakdown with respect to the 0.2% and the 0.8% in terms of loose screws versus faceplate upgrades or device replacement. This is how the maintenance cost per year played out. And once again, we looked at it from a legacy mode perspective and an evolutionary mode perspective. Definitely the legacy mode of operation on a per annum basis is more cost effective, but it's not tremendous. And I don't think that should be particularly earth-shattering, given the price points of these types of devices relative to the labor costs associated with dealing with these, either fully replacing them at 2 gigahertz or replacing them at 1.2 gigahertz. There's labor is just massively dominant in the expenditures to the tune of 85 to 90% of the total cost in either scenario. So what does this look like by the time we get to year 5 in terms of completely upgrading your network to support 1.8 gigahertz? This shouldn't be particularly earth-shattering either. I mean, we've got a 1% failure rate over 5 years. So in one instance, in the evolutionary mode, 5% of your network has already been upgraded with devices that support 2 gigahertz passband capability, whereas in the legacy mode, if you continued for those 5 years maintaining in legacy mode, you have to upgrade every device that exists in the network. So you can see in this case, there is actually a benefit by the time you get to year 5 and execute that full network-wide upgrade, that there ends up being a cost savings in adopting an evolutionary type of maintenance mode activity. And from a total cost perspective, from day 1 to end of year 5, this is how these numbers play out. So had we operated in legacy mode and waited to upgrade the network at the end of year 5, you're looking at a cost of about $12 million, $12.2 million. Whereas if you had adopted an evolutionary mode type of approach, your cost is $11.8 million. Now, it's small from a percentage standpoint, 3.2% in this case, but remember that this is all normalized to a tap device that is priced at $1. That $388,000 worth of savings is probably more on the order of $6 to $7 million that you could save over the 5-year period that we explored. So from our perspective, we fully believe that adopting a evolutionary mode of maintenance mode activity around taps and passives in your network makes a ton of sense economically. One thing I will point out that this model did not capture the fact that when you put in a 2 gigahertz device, there is no longer a loose screw issue that occurs at that location. We think actually, as we're finding out more, collecting more data, that the 1% failure rate is actually smaller than what reality is, and that technicians are visiting these locations more frequently than that. So that would only strengthen the case for the evolutionary mode of operation. We think there's obviously just some inherent advantages to technicians becoming familiar with the latest and greatest technology that's available, and seeding it into your network provides a number of operational benefits. And that is the end of our discussion. Thank you. If anybody is interested, there in the presentation material, there is a link to a white paper on this, and further, if anybody would like the model, we're more than willing to share it. So please feel free to contact me. Thank you.
Thank you very much, Jay. Georg, you've been collecting some data on this and looking at how it all sort of affects everything. How have the technicians taken to this?
So in our approach, we were collecting the end-to-end feedback cycle by the feedback from the technicians. We were just basically adding something on top of the regular business process without adding additional labor to them. We were adding some smart logic to parse the free-form text fields to work with the collected feedback.
Thanks very much. Are there any questions from the audience? Doesn't look like it. Nick, when you've looked at these connectors, as the modulation increases, can you see more problems coming from them when you go up above 2 gig maybe?
So in terms of looking at the more complex modulation schemes, yeah, absolutely. I think it becomes more apparent because you have the that shielding effectiveness changing, especially when you have sort of these RF gaps in that front face connection. When you see a lot of things going in the interface, like return loss, the 360-degree RF seal. So suddenly you are getting a bit more ingress and egress, and especially with the cell networks we have around us that can get into the network very quickly, especially if you've got these connections in the home next to mobile phones or more devices that are in the home these days. So absolutely, yeah, there will definitely be more interference where there's more traffic outside of in this case, the cable TV network and the DOCSIS system.
Staying with you, Nick, looking at, you actually mentioned moving metal. That's an interesting concept when you want to try and keep the metal still.
The displacement in the connector of the material in that sort of F-port interface, it's definitely been an interesting one to try and explain and try and look at. I think it's sort of intuitive that you don't want anything to move. You want all the interfaces to be perfect. But we've seen from the variation out there that actually they're not perfect. The materials are very different. So the fact that the shape of this F connector on a hard sort of nickel brass material being used, actually this sort of material displacement is helping. We're not scoring or we're not damaging interfaces. A lot of the surface finish that's actually applied to both the connectors and the ports is very hard. So we're not damaging the protective interface on either the connector or the port. But actually the soft material underneath is kind of being sort of deformed to fit the connector better, and we're getting that RF seal. So yes, it's a bit counterintuitive, but looking at it and the research that's come out of what we've done, all we've seen is a big benefit. And this style of connector has been out in the market for 2 years, and we've definitely had the feedback from our customers that this is going some way to overcoming some of these interface issues, and definitely seeing a sort of an RF improvement, so less ingress and egress detected.
Thanks, Nick. Arttu, in your presentation you had a point where you said attenuation is rarely your enemy under 204. Is there any case where it would be your enemy?
Well, I guess we can find out networks where you could have so long cables that it would start to be an enemy. But I think even in those networks, you have been building those networks so that you have enough cable TV signal level at home. And if you have enough cable TV signal level at home, I would say that I'm pretty sure that you don't have issues with the upstream.
Thanks, Arttu. Jay, you talk about changing faceplates. Is there any other effect? By just changing the faceplate, does that give you the total effect to be able to come up to those 2, maybe 3 gigahertz?
Yeah, there's been a fair amount of discussion around that with respect to the idea of legacy tap and passive devices that keep their bodies plumbed into the HFC network and upgrade with a faceplate that could expand the frequency beyond 1.2 gigahertz. We actually did an analysis on a number of incumbent devices and found that there's an upper limit depending on the make and model of the device, somewhere in the neighborhood of 1.4 to 1.5 gigahertz. That there's these legacy devices are really starting to hit the way they're designed. There's some design limitations that really are going to limit the ability for a faceplate upgrade to achieve 1.8 gigahertz.
Thanks, Jay. Georg, when you go through all of this, are you being able to give the feedback to the suppliers and the manufacturers as well with the information you're actually gathering?
So we have been in touch with our cable monitoring solution to get more data so that we can improve the machine learning, which is a good step. As the rules are not static but learn from the data as shown before, we want to improve them with more data that is collected upstream.
Thanks, Georg. Are there any questions from the audience? Still remains very still. Arttu, you mentioned temperature changes. Temperature changes, ice on coax cable. Does it have any effect at all?
It does. It actually has huge effect, but only in cases you have outdoor cables. So if you have outdoor cables exposed to direct sunlight, then the flux in temperatures, I mean between the extreme cold and the extreme heat, that is causing challenges to adjust the upstream amplifiers so that your levels stay ideal. So actually there, let's say you are puzzled with how to adjust them. There are solutions how to fix such problems, but this temperature variation, which is not so common in Europe as we have period cables, but in North America, for example, that is a real issue if you go to 200 megahertz return path or even up to 400 megahertz in the future.
Just going down the panel, we've seen coax has a lot of life in it now. Georg, a quick answer. How long has coax got?
It's hard to say for me. I mean, I'm more on the data side. But I guess with all of these additional improvements being made here, 70 years about the inception, I think it will last for some more time.
Nick, the same question to you.
Coming from the RF background, I'm hoping there's probably a good 10 to 15 years left in the coax. I know there's a big plan to try and get fibre out there as quickly as possible over the next 5 to 8 years. In places like the UK, there's sort of big build plans. But I think if we can squeeze some life out of the coax that's already out there, and we know how long it's going to take to build these networks, that if we can make these little tweaks that we're seeing as we're trying to put more data and more throughput through the signals, through the existing network that's there, then yeah, I think hopefully with the little bits of innovation we can have around us within the industry, then we can get a bit more life out of it. So, I'm going for a bit longer, maybe 10 to 15 years.
Thanks very much, Nick. Arttu, with your crystal ball, where do you see us?
Well, around 10 years ago, we were shutting down FM radio, as we are still battling with the FM radio. So I suppose we still have something like 20 years. But obviously, operators are gradually moving towards fiber. So it's not something that just one day everything is fiber. Let's say ratio of fiber in the networks is simply increasing, and someday the coax disappears, but I think it's still like 20 years.
Thanks very much, Arttu. And Jay, what do you feel about this?
I'm with Arttu and Nick on this one.
Thank you all very much for listening to us. Thank you to the panel, an amazing panel, really well done. Thank you very much. This will be available later today on the link on the screen. Thank you very much.